Driving Force Radio, where we seek to discover what drives today's leaders. On our show today, my co-host is Kelly De La Torre, an attorney with ALG Attorneys. How are you today, Kelly?
Great. Excited to be here, Jan.
Oh, I'm excited about this show, too. We have two remarkable leaders in the energy sector here with us today.
Yeah, this is going to be a fantastic discussion.
Tell us what we're going to be talking about, Kelly.
Today, we're talking to Kirk Sorensen, co-founder of Flibe Energy. Kirk has established himself in this arena and started his career at NASA doing technology development and working with physicists to figure out ways to use nuclear energy to power rockets to carry cargo into space.
Wow.
He also has a master's in aerospace engineering from Georgia Tech and is completing his master's in nuclear engineering from the University of Tennessee.
Wow. Yeah. Wow. This is going to be fun. We also have Baroness Worthington, the appointed member of the House of Lords in Britain. She started her own NGO called Sandbag, which is working on stopping climate change issues. She used to work with Scottish Southern Energy in the UK, as well as the UK government, and helped draft the 2008 Climate Change Act there. She's a patron at the Weinberg Foundation, and which is a foundation in honor of Dr. Alvin Weinberg, one of the original nuclear experts in the world.
Yeah, so welcome to the show, Kirk, and welcome to the show, Lady Worthington.
Yes, you can call me Bryony, that's fine.
Thank you very much. Glad to be here.
Thank you, yes.
So, Kirk, we're talking today about a type of nuclear energy called the liquid fluoride thorium reactor technology, correct?
Yes, yes.
Or LIFTR for short.
Yes.
Can you, and that's powered with using thorium?
Yes.
So can you tell the listeners, what is thorium?
That's a great question, Kelly. Thorium is a abundant, naturally radioactive element found throughout the Earth's crust and in the Earth. It's been around for a very long time. It really represents concentrated energy stored by a star billions of years ago. And in the right kind of nuclear reactors, like the liquid fluoride thorium reactor, thorium can be utilized as a very, very high efficiency energy source. By utilizing thorium efficiently, we can minimize the generation of nuclear waste, which is a very important issue. We can also use this liquid fluoride thorium reactor technology to produce very, very safe nuclear power, because these reactors do not have to contend with situations like meltdowns like we have in our existing uranium water-cooled reactors.
So what are the basic technology differences? I mean, there are major differences between the two, correct?
There are, and one way to think about it is the technologies are almost completely different between what we do today with our current generation nuclear reactors and this machine. The most important difference is that this machine uses liquid fuel rather than solid fuel, and that's really the key to its safety and efficiency. The liquid fuel is impervious to damage from radiation, which takes place in a normal nuclear reactor, and it can also be drained if you need to shut down the reactor without operator intervention or without any auxiliary power into a safe configuration. Thorium and other nuclear fuels can dissolve into this liquid fuel, and it makes it very inexpensive to both prepare the fuel and to operate the reactor and to process the fuels as you operate the reactor over time.
So Kirk, obviously there's some amazing benefits that go on with this LIFTR technology, and the technology has been proven historically, I believe. Is that correct?
We just returned from a trip to Oak Ridge National Laboratories, and one of the exciting things that the Baroness and I got to do was to tour the molten salt reactor experiment, which was one of these type of reactors that was built in the 1960s. It was an experiment that demonstrated many of the key technologies needed to make LIFTR a reality. So LIFTR is the modern evolution of the technologies that were first demonstrated there at the MSRE in Oak Ridge. It demonstrated most of the important technologies, although there are some that still remain to be demonstrated.
Okay. So Baroness, I have a question. Is the technology really ready? I mean, I guess that's one of those big arguments that's out there in this debate around LIFTR technologies. Are they ready for commercial use?
Well, no, not today. I mean, you can't just go out and build one. I think Kirk would be the first to say that I mean, there's a certain amount of demonstration and R&D we need to go through, but the length of time it takes for that to happen is really a function of what bigger priority we make it and how much resources we spend on it. So, you know, it can be brought to commercialization, I'd say, relatively quickly. I mean, not tomorrow, but over a reasonable time frame. But it's true to say, it's still not, there's no working demonstration model at the moment, but part of what Kirk's trying to do is get us to that stage so that we can get it to commercial deployment.
So Kirk, you're recognized in the U.S. as sort of a leading advocate for this technology. Baroness, can you tell us how you became interested in lifter technology?
Well, yeah, Kirk's not just an advocate within the UK, he's also reached out to communities well outside of America. And I actually met Kirk at a conference in Manchester in the UK, where we had, as part of an event put on by the Guardian newspaper, they'd invited people to come and present their ideas for technologies that could help save us from climate change. And Kirk was one of the 10 people that presented. And I can remember sitting on the panel and just being kind of blown away by the fact that here was a guy telling me that everything I knew about nuclear was probably, kind of wrong, in the sense that there was an alternative version of nuclear that had, none of the, or very few of the similarities, very different from the current situation, and it also had some extra additional benefits that I'd never heard of. So, for example, and Kirk hasn't mentioned it, but you can actually use these reactors to create medical isotopes that can be used to help treat cancers and all sorts of other wonderful sort of life-aiding. You're going to tell me it doesn't treat cancers now, aren't you?
But no, it does.
It does. Okay.
Yeah,
but exactly. So there's sort of. It's almost too good to be true, is the reaction you kind of feel when you first hear the story. And so over the last 4 years, I've kind of stayed in touch with Kirk, and we've been interrogating the idea as much as we can to see how much of it's actually true, and it's real. So that's the exciting vision is really, I think, very compelling. But the question now, I think, is mainly economic and political. That how do we get this technology out there and used? And I think as far as the engineering goes, I have no doubt that we can solve the engineering challenges, but we've got to also work on the politics and the economics.
So Kirk, I want to come back to something you said, and something that the Baroness, I think, implied. It's a new way to think about nuclear, but when you hear the definition of thorium and what it is, it's not plutonium and uranium and all of those really scary things that you think of when you hear the word nuclear energy. How is this different? I mean, this doesn't seem like traditional nuclear energy. It seems like you shouldn't be scared to have one of these in your backyard.
Yes, this is very different from traditional nuclear energy. And you mentioned uranium, plutonium. If you go and look on the periodic table, you'll find them in spots 92 and 94, and there's thorium right very close in spot number 90. So it is almost like a shadow story to nuclear power that has been in the background since the dawn of the nuclear age. One of the reasons thorium was overlooked was because it was found not to be applicable for use in nuclear weapons. And so other technologies were advanced, uranium and plutonium, and I think that's where part of that scary factor comes from. Both uranium and plutonium can be and are, of course, peacefully used and alleviate a great deal of human suffering, but I must admit there is that lingering notion of how they were used terribly in weapons at one time that it does make it difficult for the public to sort of accept forms of energy that had that connection. And thorium, fortunately, was never employed in that manner, and so probably has a neutral feeling in most people's minds. They don't really have an opinion one way or another about thorium any more than they might about dysprosium or something else on the periodic table. Nevertheless, thorium is an opportunity, if used in a liquid fluoride reactor, to achieve a very, very safe form of nuclear power. And one of the things that got me excited about this was when I first considered it was in terms of how we could use this in space, particularly in a community on the moon or on Mars. In a situation like that, we would have to think about living very, very close to your power source. This isn't something that's going to be far away, and if the power source were to fail, you're going to die really quickly. So I thought, if I was on the moon and I was totally dependent on a power source, I'd want one that I would just about feel comfortable living right on top of. And I certainly didn't feel that way about existing nuclear technologies, but I do feel that. Yeah, go ahead.
Well, no, I'm just going to have a stab at explaining kind of the thing that made me kind of understand why thorium's different from uranium is about the periodic table. And if you'll bear with me, and you can correct me if I'm wrong, it's where it's positioned on the periodic table that really makes it different. Because when you take a fissionable atom and it decays, it goes down the chain into different elements. And to the right of uranium are pretty nasty isotopes. Is that right? Yep. And if you start a couple of steps to the left along the periodic table, when it decays and the waste that it creates, it doesn't get down as far as those really nasty elements. So inherently, by starting up the periodic table by a couple of steps, you take out most of the nasties in the waste.
Yeah, that's actually absolutely correct. Thorium begins its usefulness at a spot that really reduces the formation of plutonium, americium, curium, the so-called transuranics. And that's significant because those are the elements that drive issues with waste storage. Most of the direct products of fission decay very quickly. It's those that have long half-lives and cause people a little bit of heartburn about things like Yucca Mountain. By using thorium in the right kind of machine, we can potentially arrest the formation of those in the first place and get around that issue.
There's another neat story about thorium, the element, as well. Do you mind if I say
Oh,
it?
please do.
Well, I'll try again. But I mean, a lot of people kind of, myself included, I have to say that before I started working in the energy field, I worked at Friends of the Earth, who, a green campaign group in the UK, and I was an anti-nuclear campaigner. So this is where I started this journey.
Interesting.
And so, over time, my objection to nuclear has kind of fallen away as I've got to know different aspects of it. And one thing that really helped with that was kind of realizing that, radioactive elements are not something we should be scared about. They're natural, and they form part of what sustains life on this planet. And the really neat thing is, these elements are created in the dying moments of a star imploding. They kind of wind up in our Earth. And what they currently do today is basically they're very, very prevalent. I mean, they're hugely abundant elements. Thorium's the most abundant radioactive element. And it's that's causing as that's decaying in the center of the Earth, that's keeping the center of the Earth hot, and it creates this dynamic effect where the molten part of the center of the Earth is rotating around a solid core, and that creates a magnetic sphere, a magnetic kind of protective sort of cloud around the Earth, and that's protecting us from the solar winds. So it's just actually true to say that thorium's already sustaining life on this planet by driving that dynamic effect, creating the magnetosphere, protecting us from the solar winds.
So if we go in and extract thorium from the Earth, how does that change that magnetic?
And it doesn't change it at all because it's so abundant. Yeah. We're just taking a tiny amount off the surface. This is in the center of the core of the Earth where it's really abundant as well.
We'll never deplete the Earth of thorium of any significant quantity.
And actually, Kirk always says to me he wants thorium to be reclassed as a renewable because thorium, the reserves we have of thorium will outlive the length of time that we have left with the sun, the solar system. So, that's how abundant it is. That's true, isn't it?
It's true. It's absolutely true.
Wow.
Well, to put this in perspective, you're not actually with lifter technology. If you look at Jan and I, when we're talking amongst ourselves, we refer to it as this pie. So you have all your generation portfolio, and so one piece of pie is nuclear and coal and natural gas. So you're not trying to take that nuclear piece of pie, pull it out, and put in lifter. It's more of a complement to that diverse energy portfolio, is what I'm understanding. Is that correct?
It is, and one thing to remember, we have 104 operating reactors in this country, and although we have several under construction, the rate at which we're building new reactors is not even keeping up with the rate at which we will be decommissioning old reactors. So even with a fairly aggressive schedule, our numbers are still going to be going down. That means that slice of the pie that's being generated by nuclear power is getting smaller. And if you're worried about carbon dioxide emissions in the atmosphere, then that should be of some degree of concern. The advantage nuclear power has as a generation term is it doesn't emit carbon dioxide and it's available continuously. It is a dispatchable energy source. That puts it in a fairly small category of non-carbon sources like hydro and nuclear being two dispatchable non-carbon sources. By introducing lifter technology, we have the potential to hold our line, so to speak, with nuclear generation and perhaps even to expand it, which is what I would hope for, if I may be permitted. As we drove back today from Oak Ridge, we drove by several coal-fired power plants. And the Baroness made a comment to me that I think was very significant as we drove by one in particular, the Kingston coal plant, where they had a terrible coal ash spill in December of 2008. It's cost the TVA about $1 billion. And she said, look, that's really the real enemy right there. That's what we've got to be replacing. And I said, I absolutely agree with you. We have got to be replacing our coal-fired generation. It's the #1 source of carbon dioxide emission into our atmosphere, is generating electricity from coal. There's other things, but if you wanted to solve the biggest part of the CO2 problem, you would be replacing coal with non-carbon emitting power sources.
Yeah, absolutely. And that's kind of, that's the challenge. And I think all the other technologies you described, there is a pie, but, in a sense, we don't know yet what the solution is going to be, and it's going to be a mixture of things probably. And what I like about the lifter technology is that here's a nuke that can be built that's small and modular. It can load follow, so actually it sits in alongside renewables potentially really, really well. And actually, that's the way to get to zero carbon, is to have that combination, I think, of new nukes and renewables going forward together. So that's a great vision, I think.
Well, and right now, there's a big push by the EPA here in the United States that are really forcing some of those really old coal-fired generation plants to come offline. Is there a timing issue there, since if the technology is not quite ready and these have to come online in the next 2 to 3 years, shouldn't that be a talking point to our governments to say, look, we have a great solution here, and like you say, it could be for baseload generation, it could be built right there by the load center so you don't have the transmission issues. So is there a timing issue, and is there something that we can do about that to expedite it?
And there's several questions there. Let me try to take the first one. Is there a timing issue? I think absolutely there is a timing issue, because now with these new EPA regs, there is going to be a much more forceful effort to shut down coal. And quite frankly, I applaud that, because I think we do need to be shutting down coal. On the other hand, over 50% of our electrical generation is coming from coal right now. And so we like having the lights on, and we like enjoying the benefits of all the coal. The United States has a lot of coal. So there has to be a hesitation there, thinking, how do we go and make this transition? Now you ask, will we be ready? Well, the answer is probably, the most accurate answer is no, but we aren't getting any readier, shall we say, unless we move out. And another thing that I was pointing out to the Baroness as we were driving back was how there were a number of nuclear power plants that were not completed by the Tennessee Valley Authority, that had they been completed would have allowed a lot of their coal plants to probably have been taken offline. So I almost look at it as, not only are we not on time, we're 30 years behind schedule. We should have been implementing better carbon-free energy generation technologies so that these coal plants in the 80s and 90s, when they reached the logical end of their lives, would have been shut down. Now we're in extra innings on these coal plants. They're very old, and they really, really, really need to be shut down. Unfortunately, we don't have that versatile baseload power source that's ready to go in there and replace them. And unfortunately, it's also not our light water reactor technology. It is not ready to go and pick up the slack for all these different coal sites. It takes a lot of area. There's an evacuation zone surrounding each plant that is not real fun for the people that live there. We saw a lot of signs for the evacuation zones for the plants on the way back. So I do think we're behind schedule, but waiting isn't the response to that. It is rather to go faster.
But I think the one thing we haven't mentioned in the mix is gas, and the US's emissions are going down, and we are replacing capacity by building gas, because there's now suddenly a lot more gas around, and it's very, very cheap. I mean, super cheap in the US. So there's a sort of, gas is in effect buying us some time, because every time you switch out a coal station and build gas, you get an immediate benefit in terms of CO2. And the other element that's going to play out is that they're going to probably bring in life extensions for all the existing nukes. So the 104 that we have, they're not going to shut down tomorrow, because the most economic thing to do is not to build a new nuke from scratch at the moment, but to just make sure that those existing ones can run for longer.
And could I talk on that just really briefly? That is kind of a very quiet success story that doesn't get a lot of attention, but is of great significance. Most of these plants were designed with 30-year lifetimes, and most of them reached that in the 90s, the early 2000s, because they primarily came online in the late 70s and the early 80s. So we're coming up on that 30-year timeline. What's happening, though, is they are getting these license extensions. And that has really, if you think about it in terms of what was the effect, it was the equivalent of building dozens of new nuclear power plants, which obviously didn't happen, but we also didn't shut these plants down. Now, this can't continue forever. At some point, we really do need to decommission these older reactors, and some reactors probably shouldn't get life extensions, but a lot of them are getting life extensions, and that is leading to the net effect of having a lot less carbon emission.
Well, and I guess that leads me to this next question. You know, we have the coal and gas plants that are online, and I would venture to guess the big nuclear guys that are running the plants that are already in are going to give some pushback to the lifter technology to a certain extent. I mean, they like being in charge, coal industry especially. What kind of expectation do you have around any sort of transition from traditional energy sources to this new lifter technology?
Well, it really is a situation where it's very funding dependent. Right now, our business strategy is to focus on providing power for military sites. So we are not, at this time, targeting a major civilian deployment of thorium energy. We would very much like to go more directly towards our goal ultimately, which is to have a lot of thorium energy on the grid. But it's not really in the cards right now. That, again, all those things can change with the amount of resources we mean to bring to bear. And let's not forget, and you all probably know this far better than me, just how titanic the energy sector is in our country. This is a lot of money. I mean, there is a great deal of investment out there, and in some cases, the overruns on a new plant are more than the entire development for our machines. So I look at that and I think we need some far-sighted leadership, we need some gutsy investors, we need some visionary leaders, and we need to really go for this.
I mean, the challenge is, of course, that nuclear was developed at a time when the government was throwing huge amounts of cash at it. So it had a massive startup, investment from the public purse, and those days have gone, really. I mean, and so now we're trying to find ways of, seeing how you can catalyze, public-private partnerships or something that will enable the kind of very first investment to be able to be made, because that's the hardest one, to get it over that hump of kind of initial investment where the chances of payback are riskier, and that's the big challenge. And can this be done in a system which is essentially privatized and liberalized? I mean, what's interesting is, to me, is that if you look at China, they're already moving on to this, and that's because they're more of a command and control economy. They're like we were, decades ago, and they're just saying, right, this makes sense on so many levels, we're going to invest in it. So they've put resources, money, people onto this, and I kind of hope that kind of spurs us into action, because we can now sort of check ourselves against another country that's doing it, and not to necessarily be paranoid, but to say, if China's leading the way, let's try and catch up and have a race to the top on this one.
And what happens if China succeeds first? Is that beneficial to us? Is that detrimental to us? Does it have any effect?
Well, China is a nation with over 1 billion people, and they have a tremendous need for new energy sources. Most of those people are using a tiny fraction of the energy we're using. So I certainly think that China is making a wise decision by investing in thorium. I really do hope they succeed, because they have a tremendous need for it. Nevertheless, I really hope the United States achieves parity, at the very least, with the Chinese, and even better would be to achieve a leadership position. I think there is the potential for that. The United States invented this technology. It was developed here. It was the only place it's ever been demonstrated is here. And it's logical, but unfortunately a lot of things that are logical never happen.
Well, it's interesting, when we were in Oak Ridge, it was fascinating, wasn't it? We went to the high flux reactor, which is an awesome machine. I mean, it just creates these very highly powerful kind of neutron sources, and in doing so it can create all sorts of new isotopes, and it's incredible. But the story was that it was really a PhD student who wrote it up as his thesis, this idea, and the kind of supervisor went, yeah, nice, and they looked at it and went, yeah, and shelved it. And it was only like 10 years later, when the Russians said, this is something we're going to invest in, that suddenly, the gears got moving and they started doing it. And now the only 2 places in the world that have this reactor are Russia and the US. And I think that's a really interesting, it's just a sort of almost a type of kind of collective psychology of the country, that we have to be spurred into this by perhaps being a little bit competitive.
And we had that with Sputnik too. When we saw a satellite overhead from another country, we thought, yeah, we need to have one of those too. And that built right here in Huntsville. This is the town that put our first satellite in space and helped build the rocket that put man on the moon. So.
Yeah, that exactly. So I like that. Now the fact that these guys are based here is it is like a moonshot, isn't it?
Yeah, it is. It is. And this is the only town in the world that's done the moonshot.
Well, and it's that innovation and that entrepreneur spirit that's here in Huntsville that really makes this so interesting. When we come back, we'll have more with Kirk and more with the Baroness. Kelly, we'll be right back. Welcome back to Driving Force Radio, where we seek to discover what drives today's leaders. In this segment, my co-host is again Kelly De La Torre, an attorney at ALG Attorneys. And Kelly, we're having this fantastic conversation about these new energy technologies in nuclear. And we have Kirk Sorensen, the president and chief technologist at Flibe Energy, with us. And we also have Baroness Worthington, a member of the British House of Lords, with us as well.
Yeah, it's been an amazing discussion so far, and this next half hour is going to be the same, if not better.
Yeah, it's been such an enlightening conversation. And Baroness, I want to come back to you. You know, Kirk in our last segment, right towards the end, talked about that Flibe is really taking sort of this approach at the military first to really take a rollout strategy. What does the strategy look like in the UK for this kind of technology and lifter technology?
Well, I think we're at an interesting point in the UK's kind of history of nuclear power. I mean, alongside the US, the UK has got quite a heritage in sort of developing nuclear ideas, and it had a great amount of skill and expertise. And over the years, that's kind of died away, and we've kind of settled on just allowing existing companies with existing designs to sort of come forward with their solutions. And at the moment, it's a real test to see whether that strategy is working, because the existing designs have some fundamental issues that make them pretty expensive to build, and you know, there's always going to be, I think, for me, a safety question. So, you know, I think the days of just sitting back waiting to see what the market brings forward might be changing, and I hope so that governments take a bit more of a role in steering the path that we go down, in dictating the kind of what sorts of technology they want to see brought forward. So, you know, we've kind of got a commitment in the UK to replace all of our existing nukes, and that's providing like around 16% of our electricity at the moment. And so, you know, we too are going to do life extensions, which will buy us some time. We're going to try and build a couple more of these big existing water-cooled reactors. But I think, you know, that's going to prove difficult and probably slow and maybe cost us a lot. So if we can start now thinking about where's the step change, where's the technology that's really going to change this and make nuclear play a much bigger role. And so over the next 10 years, I think we've got to really start to invest in R&D into nuclear fission, because we still invest in nuclear fusion, but that's kind of a long way off. And so really I want to see us establish a kind of government funding stream for R&D into nuclear fission, which would lead us, I think, to a much, much better technology like the lifter that we've been discussing.
Well, in your experience, how receptive is the government to those kind of conversations?
Well, they're getting more receptive, because I think for a long time it's kind of assumed, oh, well, you know, we'll just try and pave the way. We want to have 8 different new reactors built. We've identified the sites, but you know, the economics are so bad at the moment that the companies, the consortia they were hoping would build them, have one by one been saying, oh, you know, this is not looking so great, and we've had a couple of big companies pull out. So, you know, I think that the idea that we can just complacently sit back and have nuclear be replaced is changing. And so that, you know, that either then pushes you into, well, okay, we've got to do more on renewables, more on energy efficiency, more on capture from coal, and forget nuclear, or we've got to look at nuclear again and try and get it so that it's economic and easy to be built. And I would say let's move forward on all of those fronts.
Yeah, and what type of, if we're looking at sort of a rollout strategy, let's say it works for the military, and actually provides an energy security for the military, so that they could, you know, right now they're looking at developing these grids where they could be sort of, they say island in an emergency. So this would be perfect technology for that, to support that type of thing. Well, if that were to work and we could roll it out commercially, what other types of infrastructure would be involved? Because that to me is a huge cost savings, because you don't have the long transmission lines that you need for solar and wind, and since you can build it right there.
Well, what you mentioned, the idea of putting these on bases and creating a grid island, and that is often what is discussed, because they want to have energy security. They want to be able to provide power to the base completely separate for the grid, and that's mostly driven not by expensive electricity but by the need for security. But it has a really exciting effect, which is it tests the ability of a new power technology to operate this microgrid. And there might be a couple of things on that microgrid. There might be arrays of solar panels, there might be wind turbines, there might be a small reactor like the lifter doing that. And what I think could be so exciting is that could be a test bed for a much larger national grid, where you could say, here is this little world at Fort Carson, for instance, in Colorado Springs, which I know is pretty close to where we first met. It's a pretty big base, though, and they have a lot of people there, and it is like a little city. And I know they already have renewable resources on that base that they're deploying, and they have a lot of land where they're probably going to put more solar and wind resources on there. But there is a need for a baseload source, a source that can provide power continuously and one that is adaptive. So, frankly, nuclear technologies were first demonstrated, nuclear power technologies were first demonstrated in a submarine, which is an even more tight example of this little world where you need everything. I have some friends that worked in submarines that said it's the closest thing we had to being able to go into space, was to live in this self-contained world where our power and our air and everything was recycled. And I think that by having demonstrations on these bases, it then becomes more clear to the public. A lot of people work on military bases, especially here in Huntsville at Redstone Arsenal. And if they were to say, well, here's a power source that's making life really easy for us and straightforward for us and safe for us here on this site, why can't we have this in our community? Because I feel safe around it and I feel good about it. And I think it would facilitate the adoption of nuclear power. In fact, one could make the case that it was experience with Navy reactors and submarines that helped create the market and the acceptance for the current water-cooled reactors we have today, which are great submarine reactors, but not such good reactors for civilian use.
Well, and it seems like too, if you could do that kind of prove out with military here in the U.S. and abroad and whatnot, that you would see a bunch of spin-off technologies and spin-off job creation that could potentially come from that. Is that an accurate assessment or assumption, Kirk?
Absolutely, and I'm really glad you asked that, Jan, because another major difference between the lifter and existing reactors is existing reactors make one thing. They make electricity. The lifter makes electricity and a lot of other things. It runs at higher temperatures, so it has the potential to provide process heat for industrial applications. If you put one near a coastline, you could use what would otherwise be waste heat for desalination. So you could produce lots and lots of fresh water. They also produce key medical radioisotopes that are widely used to treat patients and figure out if people are suffering from different diseases or ailments. And there's other products that they could potentially produce that we've only begun to explore. And all of this is enabled by having that fluid fuel. That is the key to all of these applications.
Yeah, I just would echo that and say that one of the things that might happen is that instead of going into markets that are competing with existing technology for electricity generation, lifters could be used for industrial heat applications where there are not that many options, really. I mean, and as Kirk said, it's the fact that these things can operate at high temperature because of the molten salts that gives them that co-product of heat that can be really useful. And especially in Europe, where we've got now carbon caps that cover our industry. So if you're a big, steel manufacturer or a chemical plant, you've got to hit carbon reduction targets over time that are getting ever tighter. And there's not that many places you can turn to. You can offset and buy reductions from someone else, but actually, if you want to be conservative, you want your own low carbon source of power. And actually, using your lifter for heat could be the way out of that. So I think I hope we'll see industrial companies coming to the table in this kind of consortia that you need to build to make this happen, because they don't have all the vested interests that the current power companies have and the utilities have. I mean, and they're just looking out for what's going to suit their business model, and I think that's a potential avenue.
That is really interesting that you bring that up, because Jan and I talked about that before the show also, is that it really seems like this technology could really benefit those large industrial energy users that are constantly hit by these energy changes to our portfolio and these rate increases, and really impacts their business model. This would be a chance for them to have a consistent, reliable energy source. And is there any movement in that direction, sort of to create those partnerships and
Yes, there is, and we are actively talking with industry stakeholders along these lines, and as you've both so adeptly described, their position is not, I feel like you're displacing coal. Their position is, I need energy, and it's not just electricity, it's process heat and other products, and the potential to have a reliable, dense, low-cost, safe energy source is very attractive to them.
And I think if we had to put a bet on it, I'd hope that we could attract the chemical industry in, because they need the heat, they need the power, but also they understand the chemistry. one of the things that's held back this technology is that it's not really, the people who build light water reactors, they're physicists and engineers, and this is a whole lot of chemistry that they're not maybe so comfortable with. So it's the chemistry of it that makes it so special, but it's also the bit that existing nukes kind of go, oh, we're going into realms that I don't perhaps feel so comfortable. So we need chemistry. It's big about chemistry. So that whole industry could be one of the early adopters, I'd hope. I'm under no illusions. We've got a hill to climb in terms of, we're up against a lot of very, very powerful vested interests. The political interest is low. I mean, I actually think one of the things we need to build is this grassroots element. And, we've been talking to your colleague Kirk about the fact that, the Small Business Act that's just been signed in this country does allow you now to sort of crowdsource funding for startups. And, if we fail, and I hope we don't, but if we don't get that kind of big interest from the traditional investment community, we're going to be, I think the next step is let's see how far we can get with the crowdsourcing.
Well, and I want to come back to that. The political interest, as you said, seems a bit low, and there seems to have been over the last couple of years, at least here in the United States, a huge conversation about creating a formalized energy policy. And I don't know in the UK, but here, it's this constant back and forth about what are we doing? We need to create an energy policy that makes sense for the short term, the intermediate term, and the long term. And so it seems to me that this conversation would be striking a fire, especially in those energy conscious states and/or those states with big interests in traditional energy solutions, to either be pro or against. And we've talked about policy a little bit, but tell me, what are the barriers in the political environment, and what are those pros that we can be building on in these bigger political conversations?
Yeah, I mean, it's a difficult one. I mean, I can talk from a European perspective essentially, and say that, in Europe now there's a desire to do something around climate change that's pretty cross-party. So it's not been polarized, and so that's kind of good for investors, because they can see that whatever party's in power, the direction of travel is that we're going to try and reduce our carbon, and legislation's been put in that kind of underlines that. But I mean, it's still the price on carbon we've put on is very low. There's still not a huge amount of political will for moving fast on it because of rising prices. And so even in Europe, where we have this legislation and this cross-party agreement, the pathway for an investor is not fully clear, and there are lots of hurdles you can see up ahead. And then there's the other problem, which is that, when it comes to reducing carbon, there's lots of different technologies that can play their part. And I think governments have got to kind of tread a tightrope between, they're going to have to try, I think they need to invest in bringing things forward, doing the initial R&D, but then wherever possible, you're going to try and let the market choose, because that's the most efficient way of selecting the winners. And so we're a long way from that at the moment. We have renewables targets that specifically support renewables. We don't have any R&D in nuclear fission to get that up into a level where it can compete. And so, so it's kind of, the system is slightly rigged at the moment not to bring forward necessarily the most efficient thing. I seem to be contradicting myself in there and saying we need both federal funding and let the market choose, but I kind of think that's what's necessary. You've got to have a bit of kick-starting from government, but then, let's incentivize the broadest range of policies, technologies.
And I just wanted to touch on a statement you made, and I know, Jan, you and Kelly both know a lot more about this than I do, which is energy policy. But you're absolutely right. We don't have an energy policy in this country. I mean, this is one of the largest countries in the world, and we just essentially move about without a rudder.
And we're the largest users of energy on a per capita basis, and we just do whatever we want.
We do whatever we want, and what happens then is you sort of devolve to the least internalized cost, and I say that with that caveat because a lot of the energy sources we're using do have a high external cost. Coal's cheap, but as we drove back and looked at smokestacks, we saw the externality of that. We saw the stuff spewed in the air. How do you go and make energy source that is attractive and good for society in the long run also something that has the potential to be a winner in the market? That I really think is a great challenge, and I think that might touch just a little bit on what the fine point you were trying to make, which is there is a role for government to foster and support, but in the bigger sense, you do want a market decision and a market definition on this.
And it seems, you know, and this is in energy in general, there are just so many moving pieces of the puzzle. And a friend of mine that Sudine Kelly used to be a FERC commissioner, and she always said, you know, you always have to have a vision. You can't have a plan for energy. You have to have a vision because it's constantly changing. But it seems like things are starting to coalesce. So if you have your military application and you show that it works, that's a powerful ally to have. And then if you get private industry involved as far as the large commercial energy users, and then you also build this grassroots effort, that it seems like everything that you're doing is building that groundswell that you'll eventually reach that tipping point. I hope. And
look at their faces.
I know, I love the optimism, and I think that is the vision that kind of keeps you going. And you're absolutely right, you can't plan it out A to Z because it's infinitely complex. There's so many different parameters, and many of them are global forces that we can't really control. And so it's. I mean, I think that's why energy is so fascinating, and that's, you know, kind of where I landed. Was I started out in kind of wildlife conservation, then I got into climate change, and then I landed on energy, and I've stayed with energy because it's just so fascinating. And yeah, there's so many different levers that get pulled, but you know, taking a step back and just seeing that clearly being able to harness the power in a splitting of an atom, the density of that power, it just would be crazy for us not to try and pursue a way of doing that sort of safely and economically. And we've not really set ourselves that goal since the 1940s and 50s. And we need to redo that effort, you know, sort of go back to first principles. We know this is a hugely potentially powerful source of energy. Let's just forget everything we know and try and start again with a new set of objectives, which is let's make it the safest we possibly can and the cheapest we possibly can. And I think we'd land at a different solution. I know we would.
Well, Kirk, I know in the book Superfuel by Richard Martin, there's been a lot of conversation about thorium and the green energy evolution that's going on, if you will. I'm not going to call it a revolution because we're already sort of in the beginning stages. But he talks a lot about costs and what it's going to cost to build an infrastructure like this and to get it really going. And then, so my question is, what does it really cost? Do we have any real idea? And what does a return on investment look like for those that pay for it?
Well, the first part of that question, what is it going to cost? I mean, the most honest answer is nobody really knows. And as Baroness pointed out with energy, you don't know what's coming. You know, you have these random events. TVA didn't know that the Kingston tailings pile was going to break, and that was $1 billion down the hole right away. Fukushima nuclear reactor didn't know that there was going to be an earthquake and a tsunami. Sure. So you have these events that just throw your carefully laid plans into chaos. The second part of your question, though, which I think is the more important answer, is what is the rate of return? Because if you can have even if things cost a lot of money, if they have an attractive rate of return, investors will get into that. Right. For instance, building a new offshore oil platform is a multi-billion-dollar activity. But we do it and we invest in it because there's a pretty established path of how much it's going to cost and what the rate of return is going to look like. So guess what? Investment goes into that. It's not really about the number, it's about the rate of return, if that looks good. And you've got to achieve that number. That's really what we strive for in our design of the lifter, is to put together a business plan built around both electricity and around these co-products like medical isotopes that have an attractive rate of return to the investor, so that the capital is deployed to take you to the next step, which in turn will enable you to obtain the funding with confidence to go to the next step beyond that. You can only guess what's coming, but a good strategy is to think about, rather than addressing the market as it is or as it looks like it will evolve to, look at what the market could be and strive for that. And that's where I think the notion of lifters around the country, around the world, providing power and letting us do things that we can't even entertain right now, is the disruptive and the innovative model that is going to attract the investment and have an attractive rate of return.
The only sort of caveat I'd put on that is that there are lots of analogies sort of drawn about disruption and how this is a disruptive technology, and analogies with like Kodak and Betamax and all these other things. But the difference here is you're dealing with a nuclear reactor, so you can't just build one in your backyard and then suddenly launch it onto the market. There's an element in which you've got to kind of go through quite a bureaucratic system to get it even close to market. So, you know, I think the strategy of going through the military makes a lot of sense to me, because that's, you know, a different licensing regime, and you're meeting an absolute need that's there that's not currently being met. Then when you try and think about how to get it into the commercial markets, you know, that's when there's going to have to be a lot of work to try and make sure that this is quickly and expedited through the licensing processes. If it's as safe as we know it is, then that hopefully will be an easier task. But it's there's only so far we can go with kind of say, oh, this is disruptive and isn't it great, because actually there's a few blocks in the way of actually creating that disruption that have to be overcome.
Kirk, I want you to just look into the crystal ball and tell us, what do you see in the short term, and the intermediate term, and the long term for lifter technologies and the stuff that's going on?
You look in the near term and we see all these challenges. And part of me says, thus it ever was so. It has always been the case where the right now has seemed dark. It has seemed dangerous. It has seemed fraught with peril. The way forward has always been unclear. This has always been the experience of man, and probably ever will be. And it is only by gazing beyond that mark and seeing the world that could be, do you have the vision and the courage and, dare say, the craziness to go forward and realize that. There's a quote by Margaret Mead that I'm very, very fond of. She said, "Never doubt for a moment that a small, dedicated group of individuals can change the world. Indeed, it is the only thing that ever has."
It's our motto at ICOSA.
Wonderful.
Yeah, sorry, I mean, that's a beautiful, I couldn't agree more. And I think some things, though, that have changed that in our favour are that, you know, this small group of individuals doesn't even have to be co-located in one country or one community anymore. We're so interconnected that we can create those communities of interest around the world, and I think that changes everything.
Well, thank you guys so much. Kirk Sorensen, Lady Worthington, thank you so much for being with us today. Kelly, fantastic show. So much fun doing this.
Yeah, I have such a good time doing these shows, and this one was spectacular, so thank you so much.
Well, and to get to come to Huntsville and to actually be here and to see it and to really go one-on-one with you guys was great fun. So thank you for inviting us and having us here. Thank you for joining us for Driving Force Radio. Tune in next week. We'll see you. Have a great weekend.